So this is Robert Boyle. Not the most good-looking guy in the world, but at least he's not as ugly as Avogadro. Not nice to look at. Anyway, Robert Boyle, although unpleasant to look at, was quite a well-respected scientist, and he's kind of regarded as the first modern chemist in science. And he was responsible for discovering Boyle's law, named after him, obviously. And this law is pretty incredible, and we use it today in physics all the time, in industry and in so many amazing processes. But what it does is it effectively describes the relationship between the pressure of a gas and the volume of a gas within a closed system that remains at constant temperature and remains at constant mass. And effectively what it stipulates is a perfectly inverse relationship between the two. So as volume goes down, pressure increases proportionally, right? And the reason for that is because, I mean, if you imagine that you took 100 people and you put them in a room that was quite large, and as you condense that room, the chances of those people colliding with each other, and more importantly, the walls of that room, is going to go up significantly. And because the frequency of collisions with the walls of the room goes up, a greater pressure is exerted, right? But instead of me just talking at you like this, why don't you take a look at the tutorial video, which will help explain Boyle's law much, much better. Okay, so let's try and use our knowledge of Boyle's law to find the answer to this question. And the question is as follows. Find the new pressure of a system that once had a pressure of 25 pascals and a volume of 2.5 meters cubed. Assume the volume of the new system is 7.5 meters cubed. Okay, great. So we need our equation, right? We need P1 V1 is equal to P2 V2, right? Which is kind of an equation that was derived from Boyle's law's experiments, where he kind of demonstrated that the change in pressure is inversely proportionate to the change in volume, i.e. as one goes up, the other one goes down. Okay, and this can be represented graphically, and these are definitely some graphs that you would need to know. There's a pressure volume graph, okay, that's just a nice exponentially decreasing curve, and then a pressure against 1 over volume, which is a straight line through the origin, and that shows that there is an inverse relationship, right? If we say that P is directly proportionate to 1 over V, we can say that P is inversely proportionate to V, right? Anyway, so from these graphs and from Boyle's work, he kind of came to this equation, and we're going to use this to solve this question, right? So it wants us to find the new pressure, okay? It wants us to find P2. And we know that the pressure initially was 25 pascals, so we can say that 25 times our volume, our initial volume, which we know was 2.5 meters cubed. And obviously we need to be paying attention to this, right? It's in meters cubed. That's important. If it's not, then you need to convert it to meters cubed, right? And we know that there are 1 million centimeters cubed in 1 meters cubed, okay? Which means that if we're going from centimeters cubed to meters cubed, we need to divide by 1 million, okay? Something to bear in mind. And that is equal to P2 multiplied by V2, which we know is going to be 7.5. Okay, so we can say that 7.5 P2 is equal to 25 times 2.5, which we know if we plug into our calculator is 62.5. And then obviously all we're doing is dividing through by 7.5, so P2 is equal to 62.5 over 7.5, and that gives us an answer of 8.3 recurring pascals. Okay? And that is how we can use Boyle's law to calculate how the pressure changes in a system, or indeed the volume changes in a system, when there is a change in either of those two factors. Okay, hopefully that's helped you understand the concept a little bit better, and I've shown you the equation and the graphs and how that relates to Boyle's law. So you can go forward and apply that yourself. But remember, constant mass, constant temperature. Okay, only applies when those two variables are in play. Otherwise, things start to get a bit weird. But yeah, that's not important right now. What's important is that you like and subscribe, because we need it. Okay, so do it, and we'll see you next time on QBT. Okay, bye guys.